Okay, let's get started. As promised yesterday, part of the class will be to finish class 5 by talking a bit more about these two modes of laser machining and just a teeny bit about E-beam machining. But then mostly I will go over all of the classes and kind of point to important sections where you might expect questions from. Right, so make sure you have a pen and take notes. It can help you a lot for Thursday. So you remember last class, we went to the end of the material to explain how a laser operates, how it functions. Could anyone who was here on Monday just briefly tell us what's involved in lasing? First of all, what does the acronym stand for? Because you weren't here. The acronym stands for?
Light. I don't know what A is. Oh, light amplification. Something. No, I don't know.
Okay, you were here.
Light amplification.
Try.
Is that stimulated emission?
Stimulated, good, it's in there.
Light amplification by stimulated emission of radiation.
Good. And do you understand each of the words in there? No. So what was crucial in terms of the energy requirement in the energy levels to reach a state where you can have lasing? What was crucial in the physics of this whole thing? Whatever the active material might be, solid, liquid, or gas, something always needs to happen. Now that something is? Inversion, right. And how does that work, inversion? What do you do in inversion?
More electron, higher energy level than the lower energy level.
Exactly. And now why is it necessary? Because that was key. Why is that necessary, that you have that inversion state for lasing to take place? It has something to do with the incoming photons. Now, if you have too many states at the lower level, a photon coming in has much more chance to be absorbed rather than causing emission. That's why, right? So for those that weren't here, I need to catch up on how a laser works. Look at the end of class 5, and there's 5, 6 slides there that you need to read up on. Because it's these lasing machines that we use for laser microfabrication or laser machining. We told you there's a whole bunch of laser specific for cutting metals, plastic, ceramics, for drilling, for marking, surface treatment, welding, etc. Now, I told you that lasing, just like EDM, falls into the category of thermal machining, and both have a very bad consequence. What is the rather negative aspect on these two machining methodologies? 3-letter word.
Heat affected zone?
Yeah, this HAZ, you get the heat affected zone. And I told you that lately, people using lasing have found out a way to avoid that heat affected zone. And that's what we're going to be covering as the last section contribution here to understanding lasers in machining. What did the P and CW stand for again? Do you remember that? If you see laser and there's a P in front, it's pulsed, right? CW, this continuous wave. So we did go over this already, how a laser is made up. Okay, the next couple of slides, this is important. So the graduate students in the class need to be able to understand how you focus a laser beam. For the undergraduates, you only need to understand the result of this calculation. And so the graduates have this extra assignment tonight and tomorrow to go through these 4 slides developing the math for 2 equations. One is for the resolution of the laser, the other one is the depth of focus. So graduates need to understand how you get there. For undergraduates, you just need to be able to interpret the result. And so what we are doing here is basically calculating how small a laser beam, how small a spot can I make, depending on the wavelength and the lens that I'm using. And you can understand that's important, right? Because the smaller I can focus that spot, the better my machining will be. We also want to have a good depth of focus. Now, I will jump immediately to these equations. For graduates, I will expect you to read these slides here. And the result of the calculation you have in these previous slides are shown here. So I'm coming in with a laser, and I have a lens, and I'm trying to figure out how small can I make the laser beam. So I want to basically see that D naught there, how small can I make that? Now that expression you see there, W naught, I'm giving it in terms of radius, and D naught is in terms of the diameter. So these are really the equivalent equations. What is in it? And it should be very familiar. Without looking at it, what was the resolution in photolithography? Of course, I can't hide it, right? But what was R, the resolution in photolithography? What went in there? It's a good preparation for Thursday. So R in photolithography equals K, a constant, and then? Very good. Wavelength over numerical aperture. And look what we see here. And F over D lens is the numerical aperture. So it's the same. Kind of makes sense that it is the same, right? So the resolution of the laser, just like resolution in lithography, how small a spot I can make here in this case, depends on wavelength. So what do you want to do with the wavelength? Higher resolution means shorter wavelength, just like in photolithography. And what do you want to do with the size of the lens? Make it very big, because a big lens will lead to, in terms of numerical aperture, what will happen? Sorry?
It'll be low.
No.
No, it's over numerical aperture, so
Right.
you want it to be.
Yeah, what do you want with NA? You want it to be as big as possible, right? Numerical aperture. And that will mean a big lens. And so you will see that actually the focal distance will have the same kind of perverse relationship to resolution as we saw in lithography. So again, without looking at it, what happened there in photolithography? Resolution R. When we make NA bigger, the resolution gets better, right? A smaller number. But unfortunately, the depth of focus, what happens if the resolution gets better? Decreases. And why is that bad?
If you have a more depth of cavities or something like that, so the rays won't go till that much height.
Yeah, so if you have, in the case of lithography, if you have a thick layer of photoresist, you want to have the depth of focus at least as big as the depth of the photoresist, because the image needs to have high fidelity all the way through the whole layer. Now what it means in laser machining, over what distance can you have a nice parallel path? And so you will see here, unfortunately, when the beam becomes smaller and smaller, resolution higher and higher, the depth of focus gets worse. Just like in lithography. So that's what I want you to remember of this. And what's the consequence of a bad depth of focus? Just like before, in this case, if I want to do machining, I need to have a very flat surface. Because if I have a bumpy surface, the depth of focus isn't good enough. It will not respect the geometry, the topography of your workpiece. Good? So this you can skip. You don't need to remember these. And that's for everyone, graduates and undergraduates. Also this you can skip. And here we're coming to the important last part on laser fabrication. That's a bit of a discussion on this heat-affected zone and the big difference in using a traditional laser and then these femtosecond lasers. And so let's start with traditional laser. The most fundamental feature of a laser-material interaction in the long pulse mode. That means traditional lasers. And so that could be a pulse that lasts, let's say, 8 nanoseconds and contains an energy of 0.5 millijoule. Now follow this, this is an important point. The heat deposited by the laser in the material diffuses away during the pulse duration. Let that sink in. So during the pulse, during that 8 nanoseconds, the heat deposited in the material spreads out. And that's not good, right? Because if it spreads out, you basically are not machining and not using that energy locally. It goes sideways, right? So that is, the laser pulse duration is longer than the heat diffusion time. This may be desirable for laser welding, right? Because in laser welding, actually you want to heat and melt the whole thing. You're not looking at sharp machining, right? So this may be desirable for laser welding, but for most micro machining jobs, heat diffusion into the surrounding material is undesirable and can be detrimental to the quality of machining. Now, here are reasons why one should avoid diffusion for precision micromachining. That heat diffusion, as I just pointed out, reduces the efficiency of the machining job, right? Again, the energy is heat is not used locally, it diffuses out in the material, and the more heat conductive the material, the worse the effect is. So it takes energy away from the work spot, energy that would otherwise go into removing workpiece material. And as I just said, the higher the heat conductivity of the material you're machining, the more detrimental that effect is, and the lower the efficiency of your laser cutting. So now the link to this heat affected zone, you already get it, right? If this heat escapes the laser beam locally, the further it diffuses out, the larger the heat affected zone. So heat diffusion affects a large zone around the machining spot. And that spot, that zone I should say, is referred to as heat affected zone, or HAZ. So I talked about it before. This is the first time I kind of give you a good definition of it. And of course, this heat affected zone is not limited to laser machining. Anything that produces heat and machines via heat will have this effect. So the heating and subsequent cooling waves propagate through the HAZ zone and cause mechanical stress and might create microcracks, in some cases even macro cracks in the surrounding material. These defects then can be frozen into the structure when the material cools, and in subsequent usage you might have the part actually breaking on you. So this also, that's not only this heat diffusing out of the spot where you machine, you also have material that redeposits. It's literally like melting so violently, you will have some splashes of metal or ceramic even, splashing out of the hole you're drilling with your laser and basically causing a recast layer. Again, quite undesirable. I alluded on Monday to 2 techniques on how you could avoid that, short of using a short laser pulse. Do you remember what they were? 2 methods to avoid, to some degree, this spillover of that extra material. Do you remember them? That is the one we will talk about. Yes, I said short of that one. So there was one, it had a nice name, LACE. Remember what it stood for? LACE. Yeah, so laser-assisted chemical etching, basically what it is that hot material that gets drilled out by the laser reacts with a gas. And so it's reacted away. And so you get a cleaner surface. Another method, which they pretty much always do anyways, is to get a lot of water on the spot. And that can also avoid a bit of that heat diffusion out. So last bullet point, heat diffusion is sometimes associated with the formation of surface shock waves. And these shock waves can damage nearby device structures, even delaminate if you have a multi-layer material structure. The amplitude of the shock waves varies with the material being processed, and it's generally true that the more energy deposit in a micromachining process, the stronger the associated shock waves. So all of these negative aspects are summarized in this picture here, which summarizes what happens when you do machining with a traditional laser, where you basically have a long pulse length of about, we would see 8 nanoseconds or so. So you see some surface debris, you see a recast layer, you see that yellowish layer here, zone, is the heat affected zone, you see some cracks, you see the shock wave, etc. And in here, we're actually looking at a cut made in INVAR as an example, and you see the deposit here on both sides of this carving that was carried out. So various undesirable effects associated with long laser pulse etching or machining are illustrated here. Pulse length, as we said, is 8 nanoseconds. Energy is 0.5 millijoule. The example is a 1 mil wide carve, 1 mil, 25 microns, and it's machined in a 40 mil stick INVAR with a nanosecond laser. That's a good laser, but it's a traditional one. So now we see what happened when people introduced the femtosecond laser. This whole picture can almost be forgotten. The mechanism will be totally different. Where this is obviously thermal machining, we will see that in the case of a femtosecond laser, the whole mechanism changes. So let's read about what you can expect if you use these ultra-short pulses. Ultra-short laser pulses have opened up many new possibilities in laser-matter interaction and materials processing. Actually, for some of you that are interested in this general area, you might know this company called Aerospace Corporation. If you're interested in laser machining, laser manufacturing, there's a group there that's leading the world in a way in laser manufacturing. The leader of that group is Henry Helvation. And perhaps some of you, if you would want to go see the state of the art of laser machining, I could probably get you in to see what this man is doing. It's truly amazing. You see, he kind of has this vision that with a laser, you can make locally the material you want. Because very often, the laser actually changes the material. For example, he works with a type of glass. A glass that, if you heat it well enough, turns into a ceramic. And so literally, depending on the dose, he can change the material, then cut something, make a hole, then make a channel, then change the material back into glass, etc. So you can think how powerful this is. Not only machining, it's actually modifying the material as you go. So you might want to check that out. Henry Helvation in Aerospace Corporation, which is close by here. Just unbelievable, exciting new prospects on manufacturing. So, you know, that speaks to new possibilities in laser matter interaction and materials processing. Now, what is really happening here? These extremely short pulse widths make it easy to achieve very high peak laser intensity. Now look at that. The laser intensity can be 10 to the 14, 10 to the 15 watt per centimeter square. With a pulse of less than 1 millijoule. You should check the intensity of the sun. Can someone do that? The kind of power you get out of the sun, and just see, you might actually not be all that far off. So locally, in these spots, you reach an extremely high temperature very, very, very fast in a very short amount of time. It happens so fast that actually the pulse is over and the heat hasn't diffused out yet. Actually, what has happened, instead of melting, the material has gone into a plasma state. You went never to wet at all. You never went to the liquid stage. You immediately created a gas plasma out of the material you're cutting. So because of that, everything is totally, totally different. So the laser intensity can reach 10 to the 14, 10 to the 15 watt per centimeter square when you have a pulse width of, let's say, less than 1 millijoule. And then here you have the key thing, right? Sub-picoseconds. You remember how long the pulse was before? We talked about 8 nanoseconds, right? And that's the key difference. So here, let's read this together. And highlight the key aspects. Using these very short pulses, the laser intensity easily reaches the hundreds of terawatts per square centimeter. We just saw that a moment ago. No material can withstand such ablation forces at work at these power densities. This means that with ultra-fast laser pulses, very hard materials, even diamond, can be cut. With extremely high melting points, don't worry, it's going to cut through it just the same. The most fundamental feature, and underline that, of laser-matter interaction in the very fast pulse regime, listen to that, the heat deposited by the laser into the material does not have time to move out. So you don't have that heat-affected zone. That's crucial. So the duration of the laser pulse is shorter than the heat diffusion time, saying it one more time. And so this has numerous advantages, which are summarized in this slide and then again pictorially shown in a figure together with an invar cut that we do, same material as we did with a long pulse laser. So because the energy does not have the time to diffuse away, the efficiency of the machining process is high. Remember that? In long pulse lasing, the heat can diffuse away, so the heat is not used locally. Right? Here, it stays locally, so higher efficient cutting. The laser energy piles up at the level of the working spot, whose temperature rises instantly past the melting point of the material and keeps on climbing into what is called the plasma regime. You literally turn a solid into plasma. That's pretty amazing, no? So after the ultra-fast laser pulse creates the plasma at the surface of the workpiece, the pressures created by the forces within it cause the material to basically expand, explode, because you have created a gas. So if you create a hole here, the gases just pile out of it or pressurized out of it. So there is no melt phase, there is no splattering of material onto the surrounding material. So you can imagine that once femtosecond laser came in vogue, that suddenly the perspective of using that as a manufacturing tool dramatically improved. And here you see the difference. So that's a cut with a traditional laser. This is a cut with an ultra-fast pulse, a femtosecond laser. And look at this, no melt zone, no microcracks, no shock wave. All the heat is applied where you want it to work. So a dramatic change in perspective for short laser pulse machining. So that is what I wanted to tell you about laser machining, because I want to prepare you for the midterm. I'm sorry, I'm going to try to go a bit fast. Try to get this over here in about 10 minutes so we can go over all of the classes. I want you to read the advantages, disadvantages, and by the way, the midterm will cover also this class. Right, so do read advantages, disadvantages. It's a multiple choice, as Swati Sharma indicated to you already by email. So in that sense, you can kind of prepare for this differently than you prepare for other exams. Usually these exams, you see people leaving after 15 or 20 minutes, and that's either a good sign or a bad sign. I often notice, wow, that's fast. Take some extra time. You don't have to write things, so you can think more. It's actually a good thing for you guys, isn't it? And I will definitely not have questions in there that are language tricks. So don't be worried about that, because in the past, I've seen if you do that, some of the foreign students, in a way, suffer a disadvantage. And so there are no language tricks, like 2 double negatives or so, right? We won't do that. It will be very factual. Okay, so read through the advantages and disadvantages. Water jet guided laser machining, I touched upon on Monday. Just imagine what you do here is you have a water pipe, and you use that water pipe basically as the guidance for the laser beam. Better cooling, somewhat better machining, and you could also add some chemicals. And that again, what is it now? By now we know it. Laser. Assisted chemical etching. I forgot myself, so that's why. Line is there, man. Okay, it's just one word about this, and it's actually kind of important. It's gaining importance, and I'll tell you why. So electron beam machining is actually way superior over laser machining because obviously you can cut yet much, much, much finer structures. The big thing here is that creating an E-beam to do the machining is very expensive. It's also very slow because an E-beam operates in vacuum where a laser beam can operate in air. Right? So today, E-beam machining isn't all that widely used yet. But you might have heard that in 3D printing, more and more people now are starting to look at E-beam machines to solidify particles. So this is subtractive. Huh? I'm cutting with my E-beam. But you can also have a bed of a metal powder, and where the electron beam hit the metal powder, it can melt it and solidify it together. And so now there's actually more interest in looking at E-beam as a very powerful tool that can do both subtractive and additive. Right? And in the context of this 3D printing, this is getting kind of a second wind. And maybe people will be able to reduce the cost of this machinery. Plasma beam machining, you can just forget. I will not ask any questions about that. For those people that were not here on Monday, yesterday, this is the section that explains the laser operation. Okay, so with that, I'm going to close this off and switch computer here. And now we're going to go over all the classes. So someone has to time me here. We have about, what, 50 minutes. So someone times me so I can go through all of them. Who has a watch here? You'll time me. So you say, you don't have a watch.
I'll just do it.
Okay, so you'll time me so that I have a steady pace to cover all of the classes, okay? And so I will highlight what at minimum you should know from each of these classes, and that will overlap quite nicely with the midterm questions, which I'm still formulating. So if something comes up here, you might actually help me make the questions, okay?
How much time?
So we have what? We have 50 minutes, right? So, and I think there's been so far 10, 11 classes, something like that. So I need to, so 10 minutes per class. Did I say 10? Damn. That was bad. So class 1 was mostly definitions, right? And what I would like you to remember is all the different methods we have come up with to categorize manufacturing processes. So you can perhaps help me remember some of them. This was in terms of the energy used, right? And that's the one how we organized this whole course in terms of the energy used. But what other ones did we see? So help me out here. Give me at least 5, 6 different other ways of categorizing manufacturing processes.
Additive and subtractive.
Additive, subtractive. Top down, bottom up, yeah?
Micro, nano, anything?
That's length scale.
Yeah, batch serial.
Yeah, good, good. What else?
Primary, secondary, tertiary.
Good, yeah, right. There were probably even more, right? So let's flip through it and see if there's indeed more that we mentioned. But good, yeah, you got it. Oh, this first point here, when to apply mechanical machining versus lithography-based machining, that's when I gave you a first rule of thumb. You would switch from mechanical machining to lithography at what kind of size range? 100 microns, right? That was one rule of thumb we gave you. Here are some of the other ones. Okay, very important, the difference. Do you know the difference between relative and absolute tolerances? Right? Do you remember what that was? So for example, nanomachining, will the relative tolerance there be better than, let's say, traditional mechanical machining of a lens? It will not, right? So make sure you understand that and remember that very point. The difference between absolute tolerance and relative tolerance. Get that understood. Here were other, I think we pretty much covered all of the different categorizing means. Okay, in this curve, do you remember why the lithography progress over time and the mechanical machining progress over time are linked? I made that comment in the class. I dedicated about 5 minutes to that point. So in other words, if you look over the last century, with mechanical tools, we've been better and better at making smaller and smaller things, with lithography also. And actually both are based on the same progress in the same field. Do you know what it is?
2 years gets like half the size or something?
That's Moore's law. That's just kind of another way of saying it. But why? What's underlying there? And why lithography, which seems so different than mechanical machining, they are linked. The same thing allows progress in both fields. Do you remember what that is?
You always have to work on a table.
Yeah, very good. It's these XY positioning stages. And the better these get, and you can control the steps you can make, the better you can do your machining, be it mechanical or lithography. Remember that. Cost of machining, if I compare primary, secondary, and tertiary machining methodology, which one of those three is the most expensive one and will contribute most to the cost of your product? Third one, right? Tertiary. Good. Did I do that in 5 minutes? Is that about the right pace? 4 minutes, good. Okay, class 2. That is where we talked about this primary, secondary, and tertiary manufacturing, and was mostly about mechanical machining definition, and is about mechanical machining. Well, this is yet another categorization that we forgot to mention a moment ago, right? But that is within mechanical machining. Difference between casting and molding. Remember that? Is casting a secondary or a primary machining methodology? Primary, right? Uh-huh. Difference between casting and molding?
One is reusable and the other one isn't?
Yeah. Why are there only 5-axis CNC machines and not 6-axis machines? Remember that point? Huh?
It's one axis is a reference axis to the other axis.
I'm not. One is the. No, I'm not sure. You might think about the right answer, but the way you're saying it, these axes are not referencing. I don't know. Yeah.
The tool axis is already
Exactly right. And the z-axis usually right. This one. CNC machining stands for what again? Here is this point about the different axis machines. By the way, how many of you have done already the CNC practicum? All of you? Half of you, right? So there will not be any question of the practicum, but of course questions of the notes. What was the concept of desktop factories? What's behind that?
Streamline the manufacturing process so you have all the tools you need in one smaller spot.
Something that can also be done on a big machine. Why making it small? Transportation, but it also had something to do with the recognition that why would you use a 1-ton CNC machine to make, you know, a part that's so small? There's actually books written about the idea that there should be a ratio between the thing you make and the size of the machine. You know, it should not be like 1 million times bigger a machine than the thing you're making. So for people that have an interest in that, that's why the desktop factory idea came about. It was also the idea that the desktop factory could be owned by many more people. And so instead of having centralized manufacturing stations that cost millions, the hope is that some of these desktop factories could be much less expensive. So in a way, this 3D printing wave we see now that's so popular is kind of in the same vein, isn't it? Right? To make, we call it kind of multiple point manufacturing possible, or point of need manufacturing, you could say. The medical doctor needs an implant to be machined. He doesn't need to go in another state or to the East Coast. He could actually have it made next door. Right? That's kind of the concept behind this. So how fast did I do this one? 4 minutes. Okay, so that was this more speculative talk. And one point I was making here was that this current 3D printing, rapid prototyping, will probably not succeed the way it is. We indicated that we needed to do 3 things to make the machinery of the future much more successful. What were these 3 things? So they're behind me, so it's easy, right? But I'm going to ask you if you understand what they each mean. So we wanted to make work multi-length scales. What else? Multi-materials, multi-physics. So I'm going to ask one of you to explain each. So for example, multi-length scales, what's the idea here? Yeah, of course, it has something to do with size, but it can be a bit more specific here. Anyone can help here? What was the idea here? Yeah, think about this fractal, right? You see, if your manufacturing tool can only make things that are all between 1 and 5 centimeters, that's pretty bad, isn't it? You want something that can make sizes, multi-length scales, so let's say from microns to centimeters, right? So cover multi-length scales. Now, multi-materials is a very easy one, right? So
you can just use whatever material you need.
Exactly, because today, you know, if you're going to work with Rapidtech, you'll see that the different materials that you have access to is actually quite limited, right? So there's a lot of work being done now in developing other materials to make, instead of prototypes, functional products, right? And the third one, maybe a bit more difficult to understand, is this multi-physics. What was that about? Remember that? What was that about, multi-physics? Exactly. So multi-physics means, no, it won't be enough if you just do additive like 3D printers do today. You might, after you've done your 3D printing, you might have to polish it. You might have to do some mechanical machining. So multi-physics, you're right. Okay, for the 3D printing, besides my class, have you already gotten the introduction now to 3D printing from Ed Tackett? Has that happened already? Yes. It has, right? Was it Ben Dolan or Ed Tackett? Yeah, Ben Dolan. Ben, right? So he went a little bit beyond what I did here, but it was basically the same message, right? So if I would give you these terms here, FDM, what is it? Right, but how does it work? What's the idea there? So how does the machine work?
It extrudes the material.
It extrudes material and it works with wires, right?
Yeah, and there's a working material and a support material.
Correct, right. And I told you that across all of these 3D printing techniques or additive manufacturing techniques, there's two things in common through all of them. What is the commonality between all of these? The XYZ stage, a platform, basically, right? That can be lowered, and you layer by layer make your 3D structure. Which one of these can achieve the smallest dimensions? FDM, if I talk only about, let's say, FDM, 3D printing, and stereolithography, which one can achieve the smallest dimensions? Stereolithography. Do you remember what trick you could use to make even nano features with a modification of stereolithography? Do you remember what that was? Two-photon lithography, right? Where we literally start making structures below the 1 micron range. Of the different techniques, which one, again, and I'll compare the three prominent ones, FDM, 3D printing, and stereolithography, which one of these three gives the most functional goods, functional products? Sorry? No. Now, you remember 3D printing is kind of this powder that you just glue together, so you can imagine it won't have much strength, right? So? Yeah, FDM and stereolithography very close together. With FDM, you have still more chances of different materials, right? Because it's easier to melt something than with stereolithography. You always need to have a material that's photosensitive, right? So there's less choices there. When I introduced this fractal, I wonder how many people remember why nature ends up making in its designs of lungs, brains, trees. So many times nature uses a fractal as a design pattern. And I told you there's two reasons for that. Do you remember these two reasons?
Maximum surface area per volume.
Yes, one, but there's an, yes?
Minimize the energy required to sustain.
That's right. So one is to achieve the maximum surface area. The other one is at a minimal cost. You don't want to have too much energy involved in reaching each of the points on your fractal. I'm not sure if I illustrated that with the design of a human heart. Did I do that? Right, so if your heart were connected to your body with straight nanocapillaries, you probably wouldn't live very long. Right? A heart would have to do way too much work, and that's why the heart is configured with a big vessel that splits into two, splits up, splits up, splits up, right? What was the mathematical definition of a fractal anyways? You know that? A fractal is an object with?
Partial dimension. But
Yeah. A very key word.
Similarity at different length scales.
Yes, right. So a fractal is an object with self-similarity at different length scales. Right? Kind of means if you look at the big thing, it looks a certain way. You look at a smaller structure, it's similar to the bigger thing. So self-similar at different length scales. Right?
You're at 8 minutes.
Oh, I did 8 minutes on this one. I do want to point out something that I remarked upon with respect to this figure here. You see, almost any material we have around us is similar, isotropic, through the whole material. Now, with additive manufacturing, 3D printing, I told you we can not only make very complex products easier than traditional means, I also told you something about what you can do in terms of new materials. Do you remember what that was? We could make something that's called architectured materials. Think about that. You could have a structure that instead of being uniform dense throughout, you could have a density gradient. That's fantastic, right? That could serve all kind of purposes. And there's no other means available to actually really do that. And with additive manufacturing, you know, let's say you're going to do a polymer and it's a rather heavy, dense polymer. Well, what you can do is you can make the middle hollow, or you can make it structural with big cells, big holes. And then as you go outside, you can make the holes smaller and smaller. Imagine how would you manufacture that ever, right? So that's a very important new trend, I think, that could really catapult this additive manufacturing to prominence very quickly. Good? Okay. So from the mechanical machining techniques, we saw ultrasonic machining and sputtering and focused ion beam milling, or FIB. There's actually commonality between these two beyond both are mechanical. Both work with particles, right? Ultrasonic works with abrasive particles, maybe 5 microns or so in size, and focused ion beam and sputtering works with what particles are involved? Do you remember? Ions, right? And mostly in the case of sputtering, what ion? Usually argon, argon plus. And in the case of focused ion beam milling, gallium ion. Right? What's the difference, by the way, between sputtering and focused ion beam milling, besides it's a different ion that you use as your brick, as your tool? There's another difference.
Velocity of the particles?
Velocity of the particles?
It's not like the input energy?
Yeah, that's true, but something else.
Concentrate on one hand while sputtering.
Right, that's kind of the primary answer, right? Sputtering goes over the whole surface. And so ions hit everywhere the surface, they not being put into a beam. And in the case of focused ion beam milling, it's kind of the same process, except you make it into a narrow beam. What kind of materials would you think are the best candidates for ultrasonic machining? Brittle, what else? Very hard, right? What else? Conductors, insulators, all possible, right? Is it a fast technique?
No.
Not fast, right? Is it very expensive? Not expensive compared to any of the vacuum techniques and so on. Not expensive, actually. Look at that. $20,000, that's really not expensive nowadays as a machining tool. I mean, if you compare, how much do you think a CNC machine costs?
Depends on what size you want.
Yeah, that can be easily up to $1 million, right? So in that sense, it's not expensive. And here you have a homework question too, right? The homework question here, and please don't answer and don't bring it up, right? Don't say, oh, I know. So we want to know, why does your tool here not etch or machine faster than your machining workpiece? And we have that question both for ultrasonic machining and for EDM. So in a way, we want to know why is there asymmetry in the machining? Why doesn't your tool, in both cases, machine, corrode as fast as your workpiece, right? So that I will not ask in the midterm. Oh, very important thing here. When we are talking about the energy of ions hitting a substrate, we gave you kind of 3 numbers, right? So if I start with the lowest possible energy, if ions strike a surface at less than 1 electron volt, what will happen? And then there's a cutover, make the...
It bounces off, right? At low energy, at really low energy, it bounces off.
Yeah, all they do at low energy is just absorb on it. What's the second step? Second step is they might clean off, you know, some organic, some contamination. Third step, we actually start sputtering, right? We start kicking off atoms. Now, what about the angle of your sputtering atoms coming in? Your sputtering ions.
Looks like 45 is the best one.
Yeah, so this one, always think about billiard ball, right? So this one versus grazing angle, neither of those are very effective. The most effective is something like this, right? 65 degrees. So this is truly momentum transfer. It's mechanical in action, and that's how you know it, because of that curve. So here is this little table. So at less than 3 electron volt, we have just physical absorption. From 4 to 10 here, we have some sputtering, cleaning off of the surface. And then here, this is where sputtering takes place, let's say between 10 and 5,000 electron volts. Then you remember why this turns over? At yet higher implantation, right? So instead of sputtering off, we now start implanting ions in the solid. We gave you some important application of this. There's many applications, but what is an outstanding important application of this phenomenon?
Surface treatment?
Yes, that's correct, but there is one application out there that, you know, is really maybe the most important. No? Yeah, to dope silicon, doping to make silicon into N-type or P-type, that is what you will be using. We spent quite a bit of time on these diagrams. Of course, in a multiple choice midterm is rather difficult. I cannot ask you to draw these things, right? But I could maybe draw it and leave something out or do it wrong. Is that still multiple choice? Yeah? That's okay, right? So do you remember why there's this VP, this bias there, a positive bias in the middle of the plasma? Why is that?
Electrons move faster than ions.
Ions are
Yes.
placed between the plates, so they are mostly attracted in between the plates, rather than electrons are more focused to go away from the center, going to the display.
There's a simpler way to... Electrons, as you said, move much faster than ions, right? And so the electrons get very quickly lost on the containment walls. And you end up with something that's positively charged in the middle. I did not add that question to the homework. You remember I had a philosophical question here? If space was positively charged universe.
Yeah.
Because if it was, I don't think it is, but if it was, you know, it would mean that the universe is bounded, because the electrons could escape to the confines. And I was wondering what's wrong with that reasoning, because it seems such a simple statement.
Well, you can make the statement, but it's still difficult to prove that we're positively charged in general.
Yeah, I think that's you can probably never know, right? Because you go with a space vessel somewhere to measure somewhere way out there in space if it's positively charged, but your vessel itself probably attracts a lot of the electrons. So it's the uncertainty principle. When you try to measure it, it escapes you, something like that. Oh, very important. DC versus AC plasma. This is a DC or AC plasma?
AC.
AC, right. And so when would you use an AC plasma and when would you use a DC plasma?
Yeah, I use those.
See?
AC on insulators?
Very good, right. Now, do you remember, and this is a little bit more difficult question, do you remember why the voltage distribution in a DC plasma and an AC plasma turns out to be the same? Which is weird, right? Because you say, why should it? And so it turns out to be the same for different reasons. Now, I'm looking especially at the graduates or undergraduates, it doesn't really matter, to see if you can explain that.
The capacitor.
Sorry?
The capacitor.
Yeah? you sound like, what was it? Back to the Future. It's the flux capacitor. The capacitor, right?
So the capacitor acts as kind of like a low-pass filter on the fluctuations of the current. So for the same reason that the electrons move faster than the ions,
That created,
it's still the same argument where the electrons are going to respond faster to the fluctuations in potential.
right, I think you got it. But let's, for the whole group, make smaller steps to get to your answer. So you remember why in a DC plasma, so remove that capacitor there, and imagine this is a DC plasma. Why is all the voltage drop on the cathode?
Electrons there?
Sorry?
There's a lot of electrons there?
That, again, has to do now, and you're kind of right, and you can mimic that effect with a capacitor. The reason is the electrons in front of the cathode move faster away than the ions. So you have a big charge distribution. You have a big space charge there, and that's where the voltage drops. Even without capacitor, in that case. So now, adding to that, if you want to do etching, where will you put your workpiece, on the anode or the cathode? And why?
The negative, and I don't know which one that is.
You want to put it on the cathode. And the reason is, that's where the argon, if you see this big drop here, the argon plus ion gets all of this extra punch, right? Because it runs into that field with high velocity and knocks off atoms from the workpiece. We will later see when we do deposition, we will use the same station, we will sputter off, let's say, platinum from the cathode and deposit it on the anode. So for deposition, sputter deposition, you put your workpiece on the anode. For sputter etching, you put it on the cathode. So that's DC. Now what happens in AC? Suppose I apply an AC voltage over this without a capacitor, what will happen? It will keep switching, and so there's no difference between anode and cathode, right? They would be symmetric, right? Every half cycle, the anode turns cathode, and so forth. So you're kind of, Drew said it right, you create the same condition as in DC. In this case, you do it artificially by putting that capacitor there. Because as soon as an electron hits that electrode, that automatically will charge up. And so you, in a way, made the cathode by putting the capacitor there. We discussed this graph, right? This is the one about the efficiency of sputtering as a function of incoming angle, and then focused ion beam milling. Good? Time? 12 minutes. So, lecture 5, a little bit about soft lithography. So, I mean, one first question to put this in context of manufacturing, soft lithography, working with PDMS, is this primary or secondary or tertiary machining technique? Primary, right? Because it's a molding technique, yes.
I actually had a question about the angle of approach in whatever that was, sputtering.
Right.
Is it 65 degrees from the vertical or 65 degrees from the horizontal?
From the horizontal. And by the way, that 65 degree is a very, very crude approximation, and it differs from material to material.
Okay.
So. And so because it is so crude, it wouldn't even.
An angle, not
Right.
horizontal and not vertical.
Right. Yes, so the 65 is kind of a crude random figure. What was I just saying? Okay, about PDMS, soft lithography. Do you think that in regular manufacturing, soft lithography has a future? That's the correct answer. Who said that? Yeah, and why?
Because we produce on a large scale.
Your answer is right, but your justification is not correct. There's a more important justification. So the question is, could you ever see soft lithography become an important manufacturing technique? And by the way, it has become an important manufacturing technique, but they needed to fiddle with it. What would you have to do to make soft lithography into a real manufacturing technique? I did not teach that class, so I think Swati taught that class.
Is it the materials you can use?
No, it's something more. Look, in manufacturing, you always want to have if you have a mold and you make a part, you want it always to be the same, right? Now, if you have PDMS, which is a floppy material, and you stamp it, what do you think will happen? It will deform, and it will always be different. Yeah? And so, for research and so, it's kind of fine, but if you want to really keep very tight tolerances, it won't work. Yeah? But it's a fantastic research tool. Now, can anyone imagine there is actually a technique out there that's kind of a family to soft lithography and made it possible to really put it in manufacturing? Does anyone know? So what you would think about it, logically, to make this into a real manufacturing technique, I kind of already suggested what you would have to do. Instead of having a floppy material, yeah, you make it more rigid. And so that is exactly, what people have been doing. They have nano-imprint lithography, NIL, a very, very important technique, even being promoted as perhaps one of the next lithography techniques. Why could that, let's talk about that a little bit. So if I make that PDMS harder, and I can now really produce in big quantities, how could that possibly ever replace E-beam lithography or any X-ray lithography out there? Why would you want to do this? If you give me the correct answer, then I know you understand the power of a technique like this. What is the real power of this? It's stamping. The fact that you only need to make your stamp once, and so if that technique to make that stamp once is very expensive, who cares? Right? Because with that one stamp, you could make billions of products. And that's why a technique like this, if you make that stamp a bit tougher, could compete with lithography techniques, right? How many people have already done soft lithography lab? About half, huh? Okay. Any questions on this lithography class? Because I didn't teach it, but I have asked Swati to sit with me to formulate the questions on this part. So. Oh, damn. I don't need to do this now, right? We just finished this one. Yeah. So that's the one I kind of finished today. So I think that's it. Oh, no, I need to do, I'm sorry. Definitely need to do this one. But we'll stop it after this one. Lithography. So, some people have called photolithography 2.5D. It's not 3D, it's not 1D, they have called it 2.5D. Do you know why?
Extremely limited in Z.
Yeah. So in the XY direction, you can make any possible shape. but on the sides, it's kind of limited, right? So some people have called it 2.5D. What kind of shapes in the Z direction do you want to make? There's three principal type of shapes. Do it with your arms. So the three shapes you want to do. Do some exercise here. Good. Yeah, stand up. Right. And so how do we use each one? So Gangnam style, right? So this one, when do you use this one?
Yeah, where are we going with this?
But where are we going with this? Yeah, you could never make this one. So when are we using this one? That is when you want absolute fidelity, that's what's on the mask. You want to create that in your structure, straight walls. When do you want to use this one?
Decrease the size and the mass of the product.
Why would you ever want to use something like that? Very good, yeah. And the other one? When would you want to use that one? So I'll show these three shapes. Oh, she didn't show it, and you guys knew it. You guys are smart. She did not show that? Oh, this is good that we go over this one. So someone must have had this lithography class separately. Sorry?
She wrote it on the board.
Ah, that's why. So you think, you guys are clever. Good class. Proud of you. What is CD in the semiconductor context? It's not compact disk. What is it? Right, critical dimension. And what is it? Critical dimension? You forgot? The smallest feature in manufacturing setting that you can make reproducible, right? What is the critical dimension of the latest semiconductor chips today? Yeah, about 40 nanometers, in that range. Negative versus positive photoresist. So a good trick to remember negative photoresist. What happens when you shine light on a negative photoresist?
Part gets solidified. The part gets solidified on which light falls.
Yeah, it crosslinks more. So how to remember that is a negative photoresist is like a paint, right? So when sunlight goes onto the paint, it solidifies, right? It dries up. A positive photoresist then is just the opposite, right? The chains break up in smaller parts, so they become more soluble. Whereas a negative photoresist, where the light has struck the material, it becomes less soluble, right? Do you know which one gives the highest resolution, negative versus positive resist? I don't think we have that in the class, but maybe some of you know.
Negative.
Sorry?
Negative.
No, it's positive. Positive resist. Sorry? Yes, but I forgot. I was hoping someone would remember here. Let me think.
Would it be the cross-link dimensions?
There's a better reason than that, but I forgot. So you can ask me after the midterm. That's the privilege of being a professor. We can really forget and admit it, and then we're asking questions to you guys, and you have to have So all become professors. It's a good job. What a privilege. Huh? Oh yeah, why is this transparent material quartz and not glass? Do you know that? Why is a mask made on quartz and not on glass? Very good, right? So quartz is transparent to UV, glass is not. And as you know, for the resolution, we want to go to more and more blue light, shorter wavelengths. HMDS is a religion. It stands for His Majesty. Is it, right? His Majesty DS, what could that be? Dumbstruck. So, that was good, no? So what does it stand for? His Majesty is dumbstruck.
What does it stand for?
Yeah.
hexamethyl disulfide.
Very good, man, what a memory. Oh, it's there. And I did. Oh, you're going to do so well on Thursday. What happens when you have a silicon wafer and you let it stay in the clean room for a long, long time? What happens with the surface properties, surface hydrophobicity, hydrophilicity? What direction does it go? You know, over time, so you have a silicon wafer, what happens? So, yeah? Yeah, over time it becomes more and more hydrophilic. More and more water from the air gets absorbed, and as a consequence, the photoresist on an old wafer will not stick so good. And so what can we do for that? So we do this baking and this HDMS, right? That will make it more hydrophobic again, so that, you know, organic likes organic. With the HDMS you have these organic metal groups sticking out, and that will make a better seal to the photoresist that you put on top of it. What's the difference between soft bake and hard bake? I knew. No, so smart.
I am in grad school.
Yeah, that's and UCI.
It is conditional. One is, I mean, temperature and environment, but I mean, as far as what you...
In terms of timing of the process, I mean, which one comes first, the hard bake or the soft bake? Soft bake, right? And so principally you're removing the solvent, right? And you always want to make sure you don't go above? No. Above the glass transition temperature, right? Because otherwise the walls and the structure you build will collapse, and so it's all over. These three pictures sketch the different relations you can have between your mask and your silicon wafer. So on the left, you basically have your mask sitting on the wafer. In the middle picture, you have a small gap between the two called proximity printing. On the right, there's a lens between them. Now, when we talk about this resolution equation and depth of focus, to which one of these three does that apply? Huh? Projection only, yeah? Because, I mean, if there's no mask, you don't have a numerical aperture. I mean, if there's no lens, you don't have a numerical aperture, right? So if I compare 1 and 2, which one do you think has the higher resolution? 1. But then it's not very popular to use. Why is that? So?
Wear and tear on the mask.
Exactly, right? Because you literally have your mask sitting on your wafer, so you'll damage things. You know, you might even have some resist that's sticky and sits onto the mask, and it's over. This equation here, numerical aperture is n sinus theta. What is that n? What is? Yes, and in air it is 1. Now, I'm not sure if Swati told you about that. This simple equation gives you a means of further improving the resolution of lithography. So what could you do using this equation, right? Because this NA, you remember where that go in the expression. The expression is R, resolution is K, lambda over NA. Right? So I want to make NA bigger. So looking at that equation, what could you do? So we know we can make bigger lenses, right?
Increase the refractive index.
Increase the refractive index, very good. And so this has led to many labs around the world experimenting with something called immersion lithography. What does that mean? Well, instead of doing your exposure in air, you do it in water, where N now, instead of being 1, it becomes 1.4. And you can imagine a dramatic improvement in resolution with kind of the same equipment. So Intel, many companies around the world are trying to use that because they might get a little bit more resolution out of current equipment. I alluded to that already today, the relation between depth of focus and resolution. The better resolution, the better. I'm putting you on the wrong track here on purpose. What? The worse the depth of focus. So what is stripping? I'm going to ask the man in the audience. Is that done in a club? What is stripping?
Removing the what is it called, from
Andrew, removing, what is it called? He's still thinking about my joke. What are we removing in stripping? Photoresist, okay, good. It is a classroom. That's all for today. So, okay, very good. So from your reactions, your response today, I think you will all do very well. There will be about between 25 and 30 questions, right? And so, as I told you, you might kind of have the tendency to just run through it and chuk, and prove to your colleagues, I can do this in 6 minutes. Maybe it's not worth it. Huh? Take 8 minutes. So.